Hi, today we're going to begin Chapter 4. Chapter 4 introduces the idea behind how we form molecules and compounds. The topics that we're going to cover today in this section include differentiating and distinguishing between what we call an ionic or a covalent bond and the type of molecule or ionic substance that we form. How are they different? And the idea here is real important, is the type of that are involved in these bonding strategies. We're also going to discuss a little bit about what a chemical formula is. And simply what a chemical formula is, it shows us how these elements combine using little subscripts to represent the number of them shown in each of these substances that we're looking at. So let's begin with a review, a discussion about compounds. And what we're going to really understand in this section is what a substance is when it's combined with two or more atoms. So sometimes we can form a compound. Compounds are composed of two or more atoms of different elements. And we're going to really go into distinguishing between molecules and compounds a little bit later today, two or more atoms of different elements. And that's what a compound is. Now, as you recall from chapter 1.2, we classified a compound or a substance that's two or more atoms that are combined together as being a pure substance. And we also said, once again, that it's composed of two or more atoms. If it's a compound, these atoms are different. And we're really going to focus on distinguishing this in a little bit later today. And another important feature is that they have fixed properties. And this is going to be really important when we start discussing how we write a chemical formula and how we balance chemical equations a little bit later in this course. So we need to distinguish between types of chemical bonds in which two or more atoms may combine. And how we do this is we define them as being either ionic or covalent, as we showed on our last slide. And what we're going to need to do is be able to identify if a bond between two atoms is ionic or covalent. And we'll show how to distinguish that a little bit in chapter 4.2 in this first section that we're going to cover. So the first type of bond that we're going to look at, just by a discussion, and we'll be going into more detail on this later in chapter 4.8, is what we mean by an ionic bond. An ionic bond. So ionic bonds are formed between a metal and a non-metal. So this is really important. Metals. Now, we learned a lot about metals in our last section of periodic trends. And what's important about metals when we think of main group elements and even our transition elements, let's look at our periodic table. Just a general scheme. Doesn't have to give too much information on it. But remember, our metals sit in this region of the periodic table. These are our metals. Over here are our nonmetals. And remember some of the properties, some periodic trends that metals have in comparison to nonmetals. Well, remember, metals have low first ionization energies. And what this tells us about metals is that metals like to lose electrons. They're easy to lose electrons, and they form positively charged particles that we call cations. And I've been just talking about this for the past 2 chapters. Nonmetals on the other end of the periodic table, they share an important periodic trend. What we may recall is that they have high electron affinities. And they also have very high ionization energies. Metals have low electron affinities. So these are 2 features that help us understand how these ionic compounds are going to form through ionic bonds. Nonmetals, they like to pick up electrons, and they form negatively charged particles called anions. And this attraction between a positive particle and a negative particle is the nature behind an ionic bond. So what we need to recognize is that ionic bonds are formed from metals and nonmetals. And I have a few examples of on today's PowerPoint. We're going to learn how to name these a little bit later in chapter 4.8. We're actually going to return to these in a few minutes. KBr is an ionic compound. Potassium is a metal. Bromine, nonmetal. That's indicative of an ionic compound that's forming. Another example, calcium, and oxygen. Once again, calcium is a metal, oxygen's a nonmetal. We can infer from that they're going to form what we call an ionic bond. MgCl2. We're going to learn how to name these later. This is called magnesium chloride. This is formed from the magnesium ion, that's the cation, it's a metal, and chlorine, which is a nonmetal. Once again, these are examples of ionic compounds, metals plus nonmetals. And these properties that we learned from our periodic trends help us to understand why these form ionic compounds. Metals form cations, positively charged particles. Nonmetals form negatively charged particles called anions. And there's an electrostatic attraction between these particles to form what we call ionic bonds. The other type of bond that we're going to look at more detail and throughout this, and we're going to look at more detail of ionic bonds, are what are called covalent bonds. Now, covalent bond formation, is due to electron sharing. So covalent bonds, these are formed due to electron sharing. So how do these different from ionic bonds? One way we can think of an ionic bond is electron transfer. Covalent bonds are electron sharing. So that's a big take-home idea behind these types of bonds that are forming. And these form between 2 nonmetals, 2 or more. And one thing that this is the distinguishing characteristic of covalent bonds. Covalent bonds form molecules. In other words, molecules are formed through atoms sharing electrons. And we sometimes call these molecular compounds. But they're different. We're going to explain. Let's look at these 2 terms, molecular compounds. So substances that are involved in covalent bonding form molecules or molecular compounds. In other words, we can have 2 atoms that combine that are different elements, and therefore they're going to be considered compounds. But we can also have two elements that are the same. They're not really compounds, but they're molecules. And sometimes we say that this is how this substance exists in its elemental form. In other words, not all molecules are compounds. That's important. Let's think about some substances that we need to be familiar with that exist as what we call homonuclear diatomic molecules. Now, this is a specific example of elemental forms of substances that exist as two atoms combined together. So let's look at this wording right here. This is important, the language, the definition, the terminology. Homonuclear. Homonuclear. Two of the same nuclei. So these are just same nuclei. Homo is the same, nuclear. These are the same nuclei. And when I say same nuclei, what I mean is that these are the same elements. Diatomic, di, two atoms. Two identical elements that are combined form molecules. They're going to share electrons. There's really no propensity for an electron to spend more time close to one atom in comparison to another when they're identical. There are 7 homonuclear diatomic molecules. And these homonuclear diatomic molecules, these are how they exist in the environment, in our universe. In other words, this is how they exist in their elemental form. And I have a mnemonic to help us identify them. Hofbrinkel. And it is important to know these. Hofbrinkel. Hofbrinkel is a good mnemonic to remember our 7 homonuclear diatomic molecules. H represents hydrogen. Hydrogen exists in our environment as H2, and normally it's in the gas phase under normal conditions. O is oxygen, O2. Oxygen gas exists in our environment also. F is fluorine. Fluorine also exists as a gas in its diatomic form. Br is bromine. Bromine is one of the few of these that exist as a liquid. Iodine, it's another exception. It exists as a solid. N is nitrogen. It exists as a gas. Cl, chlorine. It also exists as a gas. So these are our 7 homonuclear diatomic molecules. These aren't compounds because by definition, a compound is composed of 2 or more different elements. These substances exist in their elemental form as homonuclear diatomic molecules. Now, to understand a little bit about why molecules form, why is there covalent electron sharing, we're going to look at the hydrogen molecule. Hydrogen is a really simple system to look at because remember, the hydrogen atom only has 1 electron. And what's real important about the formation and sharing of electrons are 2 important features. First of all is the completion of a principal energy level to give us what we call an noble gas-like configuration, electron configuration, and also energy considerations. We've discussed a lot about energy in our past few lectures. And we're going to look at both of these aspects as we think about what's happening as a hydrogen molecule forms. Again, the details behind it are going to be discussed more in chapter 6 when we introduce valence bond theory. And the details that I'm addressing are very simplistic, very much more complex than the way I will describe it. I'll leave the more complex details to a more advanced class. But for general chemistry, we need to understand two features of covalent bond formation. Remember, covalent bond is electron sharing. That's important. And what's important also in this sharing of electron density is called orbital overlap. And orbital overlap is really going to help us address the energetics involved. Let's take a profile, an energy profile. Energy is used a lot. And I'm going to draw a little axis system. And this is energy on this axis. Positive energy is an energy that's not very stable. We like to get lower energy, and negative energy is actually a more stable system. We're lowering the potential energy of a particular system by decreasing it. And to have a negative potential energy or a well is really going to be a more stabilizing feature. Let's take two isolated hydrogen atoms. They're separate from each other. And we're going to put them out here on this axis. When they're separate from each other, there's a hydrogen atom. Here's a hydrogen atom. And they're far away from each other. They're not interacting. When they're not interacting, we're just going to assume that energy is like zero. Nothing's happening between them. Let's start to bring the nuclei closer together. As we bring their two nuclei, and remember, the nuclei are close and there's a single electron in there. And there's the single electron. I'm using a negative charge. What happens as we bring these closer? And they're almost touching, is we're actually lowering the potential energy slightly. And now what's happening is this electron on the one atom is being attracted to the proton on the other atom, and this electron on the second atom is being attracted, this electron on the second atom is being attracted by the proton on the first atom. So there's some attraction between the electrons, and we're creating a somewhat stable environment. And we can think of this electron attraction between these two nuclei as almost like a glue. It's sort of bringing these two guys together. And we end up with a lowering of the total energy. We're going to have zero and go negative. And we're going to get a situation. Remember, these are s orbitals in which we have complete overlap. And we get a situation in which the electrons are now quite stable, where they're feeling the positive attraction between the two nuclei. And they're in a region now that they're like really happy, really low energy. What happens if we bring these too close together? If we bring them too close together, well, then all of a sudden the positive nuclei start to repel one another, and we end up getting this large increase if we bring them too close together. So we can think of this as this axis as the internuclear distance. Between our two atoms, and there's an optimal distance in which we have a mutual attraction between the electrons and the two protons, and we're really happy. We got a nice glue forming. So this is understanding orbital overlap. But as we said, electron sharing itself creates a very stable environment for the individual hydrogen atoms. So let's look at our two hydrogen atoms. And when they share these electrons, we're going to look at the environment of each of these now. And let's think of hydrogen all by itself. When hydrogen is all by itself, it has a single s electron. This guy has a single s electron. And now when they're sharing their electrons, well, what happens is they have their first principal energy level completely filled. And this electron sharing, we're going to learn a little bit later, is related to what we call the octet rule, which is true for almost most of our atoms. There's a few exceptions, hydrogen being one of them. Hydrogen likes to share one electron. So now when we have this vicinity around a hydrogen atom, this hydrogen atom now has 2 electrons around it. Its first principal energy level's filled, and that makes it quite stable. So for these reasons that I've explained here, we end up with covalent bond formation due to electron sharing and orbital overlap to create a more energetically favorable system. Thank you. We're going to pick up on part 2 dealing with topics in chapter 4.3.